Today we're investigating wire mortality with Arduino as our Chief Execution Officer. This is our test subject. Its life expectancy about 30 seconds. Can we use Arduino to make wires meet their dramatic end? Let's start with 100 milliamps. Apparently it takes more than that to impress our little conductor. So let's increase the current. 200, 300, 400, 500, 600, 700, 800, 900, 1 amp. At 3.3 amps it starts glowing, and the final performance at 3.4 amps. Can Arduino handle this delicate task without self-destructing? With Arduino Uno R4's modest 8 milliamp output current, it's about as threatening as a sleepy hamster. The R3 tries to flex with 20 milliamps, but that's like upgrading from a hamster to a guinea pig. Still not quite the demolition expert we're looking for. So both Arduino boards would fry themselves in the attempt. But don't worry, we're about to transform our harmless Arduino into something a bit more powerful. So we need to store some energy in order to release it later. If you open up the next decently sized electronic device, most likely you will find something like this. This is a capacitor with 100 microfarads. It can store energy and then release it later. But in order to blow up wires, we need something a little bit more powerful than that. So I'm going to use this ultra cap here. It has a capacity of 100 farads. The voltage is limited to 2.8 volts, but in my case that's not a big issue because I would like to use it with my Arduino. 2.8 volts is great. For this project I'm going to use the Arduino Uno R4 because it has a higher ADC resolution. In theory it should be able to measure the voltage with higher accuracy. I will try to use this voltage measurement to calculate the amount of energy removed from the capacitor when we explode some wires. For science. Okay, so here's the plan. I have this huge capacitor and you need to be careful with the polarity. So please connect this one to plus and this one to minus. Otherwise it might explode. So the idea is that we charge it to a certain voltage using a resistor by connecting the resistor to 5 volts. We need to be careful because this voltage here needs to be kept below 2.8 volts. So Arduino needs to constantly monitor the voltage and then stop charging once we reach our voltage. I think we don't even need 2.8 volts. We can explode this wire with less voltage than that. And in order to protect it, I will also add a Zener diode with 2.7 volts in parallel. So this way, even if Arduino is malfunctioning for whatever reason, it won't destroy the ultra cap. And once we reach our voltage, we then release it to our wire. We'll have a switch, an electronic switch, and then we will have our wire. So the switch closes and the energy flows through the wire until it explodes. As you can see, there is no resistor in the circuit, so the current will go up like crazy. This capacitor can deliver up to 74 amps. As we saw, at 3.5 amps the wire explodes, so it won't harm our ultra capacitor. So let's look at the detailed schematic. The ultra cap will be connected to ground of Arduino. In parallel, I will use the 2.7 volt Zener diode to protect it from too much voltage. In order to charge it, I will use a 12 ohm resistor. And I need to turn off charging once we reach our voltage. So I need to use a transistor to turn it on and off. For high side switching, you usually use a P-channel MOSFET. This is gate, drain and source. I will use this transistor right here. It allows a continuous drain current of somewhere between 800 milliamps and 1 amp. That's more than enough because USB is limited to 500 milliamps. And so using this resistor and a completely discharged capacitor, we get 5 divided by 12. So a maximum charging current of 416 milliamps. And once the voltage of the ultra cap goes up, this current decreases. This also means that we get quite some power here, because power equals voltage times current. And so if we calculate the worst case scenario on this resistor, we have the full 5 volts because the ultra cap is empty, times 416 milliamps, 2.08 watts. The maximum power that you can dissipate with one of these guys is something between 0.1 and 0.25. This isn't gonna work, so we need something bigger. This one dissipates more than 100 watts, so actually not that big. We can use something like this. We will connect the gate using a tiny resistor. I will use 51 ohm because I have it. I will connect this to pin 10. And here we have our 5 volts. And I will use a resistor right here. It's connected to gate as well, using 100 kilo ohm. This way, even if we define pin 10 as input, this transistor stays turned off. So if we output a low signal on pin 10, this transistor turns on. And if we output a high signal on pin 10, this transistor turns off. I would also like to have the option to discharge our capacitor. So we could use the same 12 ohm resistor to discharge it to ground. But if I connect the transistor here, then it's critical if we turn on both transistors. Then the circuit is something that I call a seppuku circuit. If we turn both transistors on, it will kill itself. So we can actually use a second resistor here. And this time we use an N-channel MOSFET, drain, source, gate. The gate will be kept low by default using a 100 kilo ohm resistor. And we use, again, 31 ohm to connect it to pin 9. And this is pin 10. So we can charge our capacitor and we can discharge our capacitor. It will discharge if we output high signal here, because if we output high signal here, then we have a difference between gate and source, and then this transistor turns on. I will use this transistor here. It has a crazy current rating of 80 amps continuous current and 280 amps pulse current. I will use the same transistor also on this side of the circuit. We have our device under test, our wire, another N-channel MOSFET to turn on the current. This one will also have a 100 kilo ohm resistor connected to ground so that it's turned off by default, and we can turn it on using a very small resistor connected to pin 11. We will also add this voltage divider here connected to analog pin 1. Why do we need this voltage divider? Because I will make use of the built-in voltage reference of Arduino R4, which is 1.5 volts. So I need to divide the voltage by 2 in order to measure it. This is what it looks like. Here we have the charging and discharging resistor. We have the ultra cap and the output transistor with the wire under test that is going to explode. Here it's very important to have thick wires because otherwise they will explode. We want this wire to explode. So this needs to be the thinnest wire here. And then on the other side, 2 transistors, one for charging and one for discharging. And everything is connected to the Arduino R4, which of course also has a nice red button. What could we do with that one? Let's write some code. So the first thing, let's measure the voltage. Let's start, and then inside of our loop we just output the voltage. But how big is the voltage? Let's use double. I'm not sure if it makes any difference. We will measure an integer, actually an unsigned integer. This one is A1. Oh, analog reference of AR internal. Analog read resolution of 14 bits. And if we use 14 bits of resolution, our maximum number is 3FFF, which is 16,383. So we can calculate the voltage divided by 16,383 and then multiply it with the ADC value. However, I have a voltage divider, so the actual voltage on the ultra cap is actually twice the amount. We can actually put in 3.0. And it's important to have at least one float number here, because otherwise it will make an integer division and it will result in complete garbage. All right, let's see what we get. Oh yeah, we need new line. So it tells me that there is a voltage of 2.5 already. I'm not so sure about this, so let's measure it. 2.3. So Arduino is measuring 2.47. The actual voltage is 2.3. I guess the difference is due to tolerances of the 1 kilo ohm voltage dividers, and maybe also tolerances of the internal voltage reference. Let's compensate it. Times 3. I will use this number here. So now we get almost the same reading. Of course, assuming that it's linear error, which I hope it is. All right, so we have a charge capacitor. So let's use the discharge circuit. One thing that we need is a target voltage. This is our target. Const int not charging pin. Not charging pin is 10, and const int discharging pin, let's call it not charge, discharge pin 9. Not discharge pin is an output, and also discharge pin is an output. Not charge pin is high in order to not activate it. Discharge pin is low in order to deactivate it. If the voltage is smaller than our target voltage, this means we need to charge. Not charge pin to low, discharge pin to high. This means we charge. And else, if our voltage is too big, bigger than target voltage times 1.05, so that we have a small tolerance. In this case, we need to discharge. So not charge is high and discharge is high. Ooh, discharge low. Yeah, like this. So we don't discharge, but we charge. And here we discharge, but we don't charge. Yeah, it's weird. Else, if we are exactly in between, then we turn off both resistors and we keep the voltage that we have. So in order to turn off both resistors, this needs to be high and this needs to be low. Yeah, now we have 2.2. So let's approach a target voltage of 2. And this looks great. The voltage is decreasing. This is actually wrong, but it still works. Interesting. Yeah. So now we're at 2.1, which means that both resistors are turned off. Yeah, we can reduce this to 1.01 so that we get closer to our target maybe. If we reduce it too much, then we get this on off, which is also bad. Yeah, this is pretty nice. We're almost at 2. And I think now we reached our target. Yeah. This looks very nice. So we keep the voltage here. We stay at our target voltage. We need something else. We need to fire, of course. We need to fire. And we're going to use this button. So now I activated the internal pull-up. We need to check if digital read button pin is low. Then we fire. So now if you press the button, it says fire. How do we actually fire? Well, we need to activate pin 11. In order to fire, first we need to stop charging and discharging. So we need to do this. That's the first thing. Then we wait, I would say 1 second. And we do a measurement because I would like to know how much voltage exactly we have. Voltage 1 equals, and we need to do this stuff right here. Now is a great time to create a function. So let's create a double cap of voltage. Let's call it read cap voltage. And we do this and we return this. So here we read the cap voltage. Then we explode. Fire using digital write pin 11 high. This activates our output transistor and destroys our wire. Then I will wait for the wire to explode. So I would say let's wait 3 seconds for the wire to explode and then turn off the output transistor so that it can charge again. And then I wait, I would say 1 second again, and then I take a second measurement, voltage 2, and this one is actually a double, and so we can then output voltage difference is voltage 1 minus voltage 2. So it's time to see if everything works. I will press the red button and we will evaporate the wire. And nothing. Interesting. Ah, yeah. We also need fire pin, of course. Const int fire pin equals 11. And fire pin needs to be an output. Now we start low. And here we use this fire pin. So let's try again. There was no voltage difference detected. So I can't really calculate the energy. But still, it was fun. Okay, great. One question that I ask myself is, can we launch rockets? In order to launch a rocket, we need to ignite the fuse. Let's add some magic cotton wool and the fuse and see if that combination helps. Not really. Now I wrapped it around the fuse. Let's see if that helps. Oh, okay, this looks great. So wrapped fuse seems to do the trick. In order to launch a rocket, we use a long cable and connect it on the very top and wrap it around the fuse of the rocket. So the rocket is ready, but it needs to be connected to this monster, of course. All right, time for a field test. I hope this works. Some debugging is required. Okay, we need more voltage. And we need a longer fire period. Come on! .7 should be enough. Damn! No, it's not. I got some smoke, but it wasn't enough. So let's see if 2 volts are enough. Happy New Year! Whew. All right, if this was interesting, then please like and subscribe to this channel. See you in the next video in the next year.